Welcome in. Our learning objective for this video is to write balanced chemical equations, including those coefficients and phases. Chemical reactions are happening around us all the time, and it's important for us to try to recognize them. Unfortunately, this can be a little bit tricky. There are some clues that a reaction might be happening, but to know for sure takes some real actual experiments and some intuition about how the atoms are moving around during these processes. For chemical reactions, we need to have different chemical structures before and after this happens. And there are some clues here: a color change, a solid formation, a gas formation, emitting light or transferring heat are clues that a reaction might be happening, but really we want to know about how the atoms are moving around. In this picture, we can see three different processes. In two of them, our chemical structures are actually changing, but in one of them, we're only changing phases. That first process is only a phase change from the solid to a gas. The chemical structure is identical. On the second two processes, we have different actual chemical bonds between our atoms, so these have to be chemical reactions. Our chemical reactions can be expressed by this chemical equation, where we show our starting materials on the left side of an arrow. We have that arrow to represent that there is something happening, and then we write our final products on the right-hand side of that arrow. All of our reactants and products are written as chemical formulas. For each of our chemicals, we want to indicate how many of each is required. And we'd also like to include the phase for each of our chemicals. Our phases can be expressed as parentheses G or L or S. We've seen those before. Or we have this other one, parentheses AQ, which means dissolved in water. We need to represent the amounts in our chemical reaction because we want to obey that law of conservation of mass. We want to obey Dalton's atomic theory. Our atoms are only going to be rearranged when we do our chemical processes. They're not going to be created or destroyed. Because of that, we need to have the same amount of each element on the left side of the arrow as we have on the right side of the arrow. Our example down below, we can make a tally. Do we have the same amount of each atom? On the left side, we have just a single carbon. On the right side, we also just have a single carbon. For our hydrogen, we have 4 on the left. And on the right, we have just 2 hydrogens. On the left, we have 2 oxygens. On the right, we have 2 oxygens, plus another 1 for a total of 3 oxygens. Is this balanced? No. We've had 2 hydrogens disappear, and we'd have an oxygen show up out of nowhere. This doesn't work. This is actually no good. Here we can visualize this. We have our three-dimensional picture of these molecules. We can count up the number of each type of atom. There's a problem here, right? We don't have the same amount of hydrogens or oxygens before and after this reaction. To fix this, we can adjust what we call coefficients. We put numbers in front of our chemical formulas to show the amount of those chemicals. Here we put the number 2 in front of this oxygen to show that we have 2 of that entire molecule in front of it. Likewise, we put a 2 in front of this water, H2O, to show that we have 2 of this entire molecule. Now we can count up our atoms and see that we do have the same amount of each before and after this reaction. We can do that tally method again. Here we have 1 carbon on the left, we have 1 carbon on the right. We have 4 hydrogens on the left, and we have a total of 4 hydrogens on the right. This 2 in the front multiplies all of our coefficients down below. Lastly, we have 2 times 2, so we have 4 oxygens to start with. And we have 2 plus another 2, so 4 that we end with. This is what we call a balanced reaction. We can do another example like this. Here we have photosynthesis, and it looks like we again have just carbon, hydrogen, and oxygen. Right now we have 1 carbon to start with and 6 carbons that we end up with. Right now we have 2 hydrogens turning into 12 hydrogens. And we have 3 oxygens turning into 6 plus 2, 8 oxygens. We need to start fixing things. And so if we just start at the beginning, we can fix our carbons. Instead of 1, we want to have 6. We can't change the subscript because that will change the identity of our molecule, but we can change the number in front to make sure that we have the same total amount of atoms. This also changes the amount of oxygens, so we can update our tally here. Now we have 12 plus 1 is 13. And this is getting us closer to a good answer. Our next step can be to fix our hydrogens. We want to have 12 instead of 2. Again, if we add a 6 here, we end up with 12 hydrogens. Once again, this disrupts our number of oxygens. So now we have 12 plus 6, we have 18 oxygens. And once again, we're a step closer to getting a good final answer. Lastly, we need to adjust our oxygens. We're looking to have 18 oxygens. Right now we have 6 from here, and we have some number times 2 from our O2 molecule. We need to get this to add up to 18. It looks like our value here, I called it that question mark, has to be 12 divided by 2, which is just going to be 6. There we go. Now we have a nice balanced reaction. This is like a nice recipe. 6 carbon dioxides react with 6 waters. When this happens, we get to build 1 of our glucose molecules and 6 oxygen molecules. Let's outline our strategy. We can start by writing what we call a skeletal equation, one where we only have our chemical formulas. This is unbalanced, but that's okay. We can do what we just did to adjust our coefficients to end up with a nice balanced reaction. Step 2, we can start adding those coefficients, changing those coefficients. Some tips here. Let's start with elements that appear just once on each side. Start with our compounds that are more complicated. If things are simple or show up multiple times on the same side, we can leave those till the end. Number 3 is a tip here. If you have polyatomic ions that stay intact throughout the reaction, we can keep track of our polyatomic ions instead of our elements. Lastly, step 4, if you keep that tally, you can check your answer at the end, make sure everything adds up the same at the beginning as it is at the end. This is a nice example that has polyatomic ions. We have some NH4+ that is remaining as NH4+. We have ammonium that is not being broken apart, it's just being moved around. Likewise, we have hydroxide that is not being disrupted, it's only moving, changing what it's bonded to, but it's still existing as those hydroxides. Then we have our nickels and we have our chlorine. We have our pieces identified. Now we can tally them up and try to balance. 1 ammonium to start with, 1 ammonium to end with. 1 hydroxide to start with, 2 hydroxides to end with. 1 nickel that we start with, 1 nickel that we end with. 2 chlorines turning into just 1 chlorine. All right, this does not quite work as it is right now, but we can change some coefficients and make it better. We can start by saying we need 2 hydroxides. The only way to do that is by adding coefficients. Since we changed the 2 in front of NH4OH, now we have 2 ammoniums as well. On the right side, we need to fix the number of chlorines. Again, we can change this coefficient out in front. Oh no, this changes the amount of ammoniums on the right. Well, actually that's good. Now we have 2 to start with, 2 to end with. 2 hydroxides on both sides, 1 nickel on both sides, 2 chlorines on both sides. This is nice and balanced. We have a question here for practice. So why don't you grab some paper, write down some good answers, see if you can get this on your own. There we go. We've learned how to write balanced chemical equations by adjusting those coefficients. Don't forget to include your phases for each chemical you find. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.